For centuries, we've looked to the skies and dreamed of flight. From Da Vinci's earliest sketches to the thunderous roar of a supersonic jet, it's always felt like our quest to conquer the air has been about pushing engineering to its absolute limit. But here's what most people don't realize. The next great leap forward in aerospace might not come from a futuristic lab at all. It might just be hidden inside a blueprint that's 150 million years old.
So, let's start with a question that sounds a little crazy. What on earth could a vulture's wing possibly have in common with a top-of-the-line fighter jet? Well, the answer is a truly brilliant piece of engineering that solves one of the single biggest challenges in all of aerospace.
You see, it all boils down to this one critical concept, the strength-to-weight ratio. It's a brutal trade-off. Imagine you need to build something that's as strong as a tank, but as light as a feather. Every single ounce, every gram, it all matters. You need materials that can withstand unimaginable forces but weigh almost nothing. It's the ultimate puzzle for engineers.
And to win this fight against gravity, our own ingenuity has come up with some solutions that are, frankly, mind-bending.
And make no mistake, this isn't some niche scientific hobby. We're talking about a colossal industry. By 2029, the market for these advanced materials is projected to be worth nearly $43 billion. All of that money, all of that brain power, is focused on shaving off just a few more grams to make flight more efficient and to push the boundaries of what we think is even possible. The absolute cutting edge of this whole quest is something called architected cellular materials. Now, forget just mixing different metals together. We are now talking about building materials from the inside out, designing their internal structure, their architecture, like a microscopic city, to give them properties that seem almost supernatural. Take a look at this. What you're seeing is one of the lightest metallic materials ever created. It's called an ultralight metallic microlattice, and even though it looks like a solid cube, it's actually 99.9% empty space. It's a delicate yet unbelievably strong web of tiny hollow tubes. Using incredible technologies like advanced 3D printing, we can now create these unbelievably complex lattices out of titanium alloys, structures that you just couldn't make using traditional methods like forging or milling. We are literally building strength atom by atom. And when you zoom in, the level of precision is just staggering. This polymer structure was built using light, layer by microscopic layer, creating an internal architecture that is perfectly optimized for strength. It is an absolute marvel of modern engineering. But this is where things get really interesting. This futuristic idea, it's not new at all. In fact, you could say that nature perfected this exact design principle more than 150 million years ago.
Meet nature's masterpiece of lightweight engineering, the bird bone. On the outside, it looks pretty simple, right? And we've all been taught that bird bones are hollow just to save weight. But you know what? That's only scratching the surface. The real genius is hidden inside.
To get this, we need a super quick physics lesson. When you take a solid rod and you bend it, almost all of the stress is concentrated on the very top and the very bottom surfaces. The material right smack in the middle, the core, well, as this quote explains, it really isn't doing much of anything. It's just dead weight. So what was evolution's elegant solution? It was brutally efficient. It just got rid of the part that wasn't working. By hollowing out the core of the bone, nature ditched a huge amount of weight. But that brings up a really important question. How does a hollow tube not just get crushed under pressure? The answer is in this beautiful, complex internal structure called trabeculae. The best way to think about it is like a microscopic scaffolding. It's this intricate web of tiny struts and braces that reinforces the hollow bone from the inside out. And there it is, the connection that changes everything. On one side, you have our most advanced billion-dollar man-made materials, and on the other, the inside of a bird bone. Look at that. The principle is identical. A hollow structure designed to distribute stress, reinforced by an internal lattice for lightweight strength. We haven't invented something new. We've just rediscovered a 150 million-year-old design. So how does this natural marvel actually work in practice? Well, during flight, as the wing bends, the forces try to squeeze the hollow bone and flatten it out. But those internal trabecula, they act like a perfect system of cross braces. They literally push back against the walls, keeping the bone's shape and preventing it from buckling under pressure. It's an incredibly simple and elegant solution to a really complex problem. This kind of realization is pushing engineering into a whole new era, one where we don't just invent, we listen. We learn from the genius that's all around us in nature.
This is the incredible power of what we call biomimicry, and it's not a one-off thing. Nature's designs have been stress-tested over millions of years of evolution. They are ridiculously efficient, and by studying these blueprints, we're not just copying nature, we're learning from its eons of research and development to build better, more sustainable technologies ourselves.
So, the next time you see a bird soaring effortlessly overhead, remember this: the very same principles that allow it to fly are now inspiring the next generation of our own aircraft. The future of our most advanced technology, as it turns out, might just be written in the bones of the past.
It really makes you wonder, doesn't it? If the secret to next-generation aerospace was hiding inside a skeleton all this time, what other revolutionary blueprints for technology are out there, just waiting to be discovered, hidden in plain sight all around us?
Don't go anywhere, hit subscribe and we continue.
For decades, we've been looking up at the stars, totally convinced that the peak of engineering was out there, in the silence of space. We build these incredible machines to fight gravity, to survive in a vacuum. But what if the most advanced technology in the entire universe isn't in some distant galaxy we're trying to reach, but right here, in the world we've been trying to leave behind? Now, I want you to just let that sink in for a second. This isn't some poetic line from a nature show. This is from a NASA technical memorandum. The same people who put rovers on Mars and flew by Pluto are literally looking at life on Earth and saying, yeah, they do it better. That one sentence, it's a clue. It points to this huge shift in how our top minds are thinking about technology. NASA isn't just admiring nature from a distance. For years, they've been quietly and systematically trying to decode the biological world. It's like they're treating it as a library of advanced, almost alien technology that's just been sitting here the whole time. They're becoming code breakers, trying to reverse engineer 3.8 billion years of research and development. Okay, so let's get into what this really is. This entire field, this art of basically stealing from nature's playbook to solve our toughest problems, it has a name, and it's the key to this whole story. It's called biomimetics. And yeah, it sounds a little academic, but think of it more like a team of, technological archaeologists. You've got biologists who can read the living blueprints, material scientists who figure out what everything's made of, and engineers who can take those ancient designs and build them today. It's one team, all focused on a single mission: learn from the undisputed champion of engineering, life itself. So what is it? What are these secrets that have the world's most advanced space agency taking notes? Well, to understand that, we need to open up some of nature's case files. And you'll see, the answers have been hiding in plain sight all along. All right, let's look at 3 specific cases where nature's quiet genius is directly changing the future of our own technology. And these aren't just cool ideas. These are active areas of research with millions of dollars behind them. First up, a problem that's as old as movement itself: friction, drag. For anything moving through air or water, drag is the enemy. It's this invisible hand that just wastes energy, makes us build bigger engines, and costs the world billions and billions in fuel every year. We've spent a century of engineering trying to beat it. The shark, though? It solved this problem way before the dinosaurs even showed up. Now, what's so amazing here is that it completely debunks what we all think. Shark skin isn't smooth at all. It's this incredibly complex surface covered in millions of microscopic tooth-like scales. And these tiny little structures, they actually manipulate the flow of water right at the surface, breaking up the little vortices that cause drag. NASA has actually confirmed that copying this pattern can cut down friction by 6% or even more. Now, 6% might not sound like a lot, but apply that to a 747 or a nuclear submarine, and it's a massive leap in efficiency. Let's move to our next case. The problem? Noise. Think about it. Our most powerful machines, jet engines, giant wind turbines, they literally scream their existence into the world. They're all about brute force. But in nature, the deadliest predator of the night has figured out the exact opposite: true power through silence. An owl in flight is a ghost. It's absolutely silent. And the secret is this beautiful 3-part system in its wings. The front edge has this stiff, comb-like fringe that breaks the air into tiny, quieter streams. The top of the wing has a velvety texture that just soaks up sound, and the trailing edge has this soft fringe that smooths out the airflow as it leaves. Engineers are now copying this exact design to make fan blades that can move huge amounts of air in near total silence. It's incredible. And for our last piece of evidence, we're going to tackle a huge dilemma in material science, the classic trade-off between something being strong and something being tough. You can usually have one or the other. Ceramic is super strong, but it's brittle, it shatters. Kevlar is tough, but it's flexible. Nature, on the other hand, well, nature doesn't see why you can't have both. And this is where it just feels like nature is showing off. This is nacre. It's the shiny stuff on the inside of a seashell. Now get this, it's 95% calcium carbonate. You know what that is? It's chalk. Literally, one of the weakest, most brittle materials there is. But by arranging that chalk into this microscopic brick and mortar pattern, held together with just a tiny bit of organic goo, nature does something amazing. It creates a material that is thousands of times tougher than the chalk it's made from. This structure, which stops cracks in their tracks, is the blueprint for the next generation of materials for aerospace. So we've looked at these incredible individual tricks, the shark skin, the owl wings, the mollusk shells, and it's really easy to look at that and think, okay, cool, that's the story. But if we stop there, we completely miss the revolution that's really happening. The real game changer here, the secret that NASA and others are really trying to unlock, isn't just about copying individual parts. It's about copying the entire operating system of life itself. So look at what defines every single living thing on this planet. Biological systems are robust. They can take a hit and keep going. They adapt. They're autonomous. They can repair themselves. And they are absolute masters of using energy efficiently. These aren't just features that get bolted on. These are the core principles of nature's design language, written into every single cell. This is the ultimate goal. See, NASA doesn't just want a wing coating that's inspired by a shark. They want a wing that can actually sense turbulence and change its shape on the fly. They don't just want a composite material like a seashell. They want a spacecraft hull that can detect a tiny meteoroid impact and literally heal the damage itself. We're moving from building static machines to growing adaptive, almost living systems. That is the new frontier. So this whole journey into biomimetics, it reveals a pretty incredible truth. It shows us that the answers to some of our biggest technological problems, from energy to materials, they might not need to be invented from scratch. Maybe they just need to be discovered. And that really leaves us with one final thought. For generations, we thought that the next giant leap for mankind meant looking up at the stars. But maybe, just maybe, the next truly giant leap will be made by looking down at the quiet, brilliant, and impossibly smart life that has been perfecting its designs on this planet all along.
Don't go anywhere, hit subscribe and we continue.
How in the world does a gecko just casually walk up a sheer pane of glass? Or how does a spider web, something so delicate, manage to survive a raging storm? Well, these are just incredible marvels of natural adhesion. But here's what most people don't realize. The true genius isn't one single secret. It's a whole toolkit of surprising and frankly brilliant solutions. So let's dive in. It's a pretty humbling thought when you stop and think about it, isn't it? I mean, while we've been building and inventing for, a few thousand years, nature has been running the most massive R&D program in the history of the planet. Every living thing you see is a masterpiece of problem solving perfected over eons. And when it comes to the simple, fundamental problem of just sticking to things, well, nature's solutions are nothing short of genius. Okay, so let's start with the absolute icon of adhesion, the gecko. This little guy is the poster child for an impossible grip. For centuries, its ability to just defy gravity was a complete mystery. So how on earth does it pull off this trick? Right, so the secret isn't some kind of super glue or tiny section cups. It's pure physics, happening at the molecular level. It's all thanks to something called van der Waals forces. Now, these are just the tiny, fleeting attractions that happen between any two molecules. Individually, they're almost nothing. So the gecko's secret isn't about the strength of the force, but its absolute mastery of quantity. And this is how it does it. This is the truly brilliant part. Its feet are covered in millions of these microscopic hairs called setae. But wait, it doesn't even stop there. Each one of those hairs then splits into hundreds of even tinier nanoscale tips called spatula. This tiered hierarchical structure is it's pure genius. It lets the gecko's foot conform to literally any surface, no matter how smooth or rough, creating a massive surface area and turning billions of those tiny, weak forces into one unbelievably strong bond. Just how strong are we talking? Well, theoretical calculations just based on the number of setae on a single tokay gecko's feet suggest it could support up to 130 kilograms. That's about 287 pounds. To put that in perspective, that's more than enough to hold the weight of a full-grown person. It's just an astonishing feat of natural engineering. And that, right there, leads us to the crucial question. If the gecko's physical, reusable grip is that powerful and so versatile, why isn't it the universal solution? Why would evolution ever bother to invent a different way to stick? This is where the story gets really, really interesting, because the gecko, as amazing as it is only chapter 1. To understand this, we have to look at where the gecko's solution might actually fail, because a grip that works on a cool, dry wall might be totally useless somewhere else. You see, nature doesn't design a master key. It forges a very specific key for every single lock it encounters. So let's just compare two scenarios. You've got the gecko, which needs a reversible adhesive, right? It has to attach and detach its foot in milliseconds just to be able to run. But now, picture this, a tiny canopy ant, living 100 feet up in the tropical trees of Panama. Its world is a scorching hot leaf surface, where a delicate physical grip like a gecko's, it just might not hold up. The ant faces a completely different challenge, extreme heat. So the ant's solution is pure chemistry. On a leaf surface that can get incredibly hot, those delicate nanostructures on a gecko's foot would probably fail. So what does the ant do? It secretes its own specialized biopolymer glue from its feet. It's an adhesive that doesn't just tolerate the heat, it's literally optimized for it. And you have to remember, for these wingless worker ants living 100 feet up, falling is not an option. There is no backup plan. Their glue has to be absolutely 100% flawless. Now let's talk about another master engineer, the spider. A gecko sticks and unsticks, but a spider needs to build a permanent structural anchor for its web, and its solution is a masterpiece of material science. It's not just a glue. It's a composite cement spun from something called pyroform silk. Okay, think of it like natural reinforced concrete. It's got a strong protein core for tensile strength, which is then coated in a nanofibril glue for adhesion, and then it's laid down in a mesh pattern that brilliantly stops tiny cracks from spreading. This is what we mean by flaw tolerant. It's engineered from the ground up to resist catastrophic failure. It has to. So let's step back for a second. We've got a reversible physical grip, a heat-proof chemical glue, and a flaw-tolerant composite cement. And this is where the hidden truth of it all starts to emerge. What we're really looking at isn't one perfect invention. It's an entire, highly specialized toolkit. This table just lays it all out so beautifully. You've got the gecko with its physical grip, perfect for versatile, reusable sticking in dry places. And what do you know? That's why NASA is developing gecko-inspired grippers for robots. Then there's the canopy ant's chemical glue, designed for extreme heat, which is inspiring brand new high-temperature adhesives for our own technology. And finally, the spider's composite cement provides this incredible flaw-tolerant structural bond, pointing the way towards new biodegradable medical biomaterials. Each one is a different tool for a different job. And here it is. This is the crucial point, the detail that changes everything. The real secret to nature's genius isn't the gecko's foot. It's the fact that the gecko's foot, the ant's glue, and the spider's cement all exist at the same time. Nature's true brilliance wasn't finding one perfect solution, it was in building a diverse portfolio of perfect solutions, each one precisely engineered for a totally different problem. That is the real lesson here. So, this is where it all comes together for us. By studying this incredible toolkit, we can finally start to tap into that 3.8 billion years of research and development. We're moving beyond just mimicking the gecko and starting to learn from nature's entire portfolio of adhesive technologies. And this is not science fiction. Listen to this quote from NASA about their gecko-inspired grippers. They said, "The grippers don't leave any residue and don't require a mating surface on the wall the way Velcro would. They're developing adhesives that are not only strong, but also reversible and clean. No sticky gunk left behind. They're even testing them for astronauts to use on the International Space Station. How cool is that?" The applications are just incredibly exciting and so diverse. We're seeing gecko-inspired grippers for manufacturing and space exploration. We're developing prototypes of ant-inspired glues that can withstand insane temperatures. And we're creating spider-inspired biomaterials that are both super tough and biodegradable. We are finally learning to pick the right tool from nature's toolkit to solve our own engineering challenges. It just makes you wonder, right? We've just looked at 3 different ways nature solves a single, simple problem: how to stick. But nature has solved millions of other problems with the exact same level of genius. So what other revolutionary technologies are just waiting for us out there, hiding in plain sight, if we only know where and how to look?
Thanks for watching. Support BioVellum by liking, subscribing, and sharing. Let's explore the secrets of nature together.